today's section 7.4 on compounded interest. You can see we're going to be able to solve real-world problems, definitely, that model expressions with these different powers in them. And then we want to be able to apply the compound interest formula. So knowing that, let's get started with some money. Compound interest. We should be looking at the idea that when you have money and it is growing, set away in some kind of institution, bank, credit union, whatever, and it will grow based on what the bank will give you in terms of interest. Now, the interest that they give you is an annual rate. So the rate, whether it's 5%, 2%, 6%, is an annual rate. But how many times they will actually compound is what will benefit you in the long run. So annually is a situation where we know it's yearly, and so our money will get calculated once every, or our account will get calculated once every year. Where general compounding means we could do it more than once a year. So the big difference in these two problems, as you can see here, would be the n value is present here. Whoa, that's a little big. It is present here and here, and it is not in the other two. But think about it. If your annual interest rate was 1, where that n is in the other equation, it would be r divided by 1. Well, anything divided by 1 is just r. And where that n is in the exponent look, if n was, again, 1 time per year that we were doing it, 1 times t is just that t value anyway. So it's going to be up to you whether you want to memorize 1 or 2 equations. Yes, you can use the annual down in the lower one as long as n equals 1 when they say annual. So you can use the annual idea of n equals 1 in the general compounding rule and then only memorize the 1. But that n factor is key. It is the only factor that occurs twice, notice, and it has to be the same number in both cases. Now, with that many variables, let's double check everybody understands the different combinations. A is the total amount of money in your account. That would be how much you put in, interest, everything. P, the principal. That's the total amount of money you're going to invest. In some cases, some people would say borrow. We're going to do the other situation. R, the interest rate written as a decimal that the bank will give you annually. And then N, the number of times per year the bank will calculate that interest. And that is the compounded value. T is the length of time of your investment in years. So is it going to sit there for 1 year, 10 years, 20 years, or more? Or maybe it's going to only sit there for 18 months. If they ever give it to you in months, make sure you do the conversion back to years, because it has to be time in years in order to use this formula. Okay, with that, let's talk about those compounding values real quickly, and then we'll do a couple problems. So we said if we are compounding, and we are compounding annually, we have an n value that is 1. If it's semi-annually, the bank will calculate our account twice a year. Semi, half, so it'll do it at every 6 months interval. Quarterly, we know there's 4 quarters in a whole, so we would say that it's going to be, some people says, well, that's every 3 months. Yes, it is, but still the whole point is they will do it quarterly, so they will do it 4 times per year. Monthly, every month, we know there's 12 months in a year, so that will end up being, n would be 12 times that the bank does it in 1 year. Weekly, we know that's 52 weeks in a year, so 52 different calculations would be done. And then daily, we like to go with the 365. We're not going to go with anything astrological. Okay? So those are typically the ones you're going to see. And those would be the N values you use on a regular basis. So let's look at each of these here and see what our calculation would be. So using our same formula, you must invest $4,000 into an account that compounds interest annually and pays 6.2% interest. How much do you have after 4 years? So right away you're going to say A equals, our p-value in this case is that 4,000 we're going to invest, times 1 plus our rate was 6.2%, but you don't calculate with a percent. You change that to a decimal, make it 0.062, 0.062, all divided by our N value. Compoundings in this case is the word annual, so that'd be a 1. So if you don't want to write the 1, that's fine. To the power of 1 times t. We're going to leave it sitting there for 4 years. So I like to multiply it out whenever possible so I don't have two numbers sitting there. So we say to the power of 4. So go ahead and calculate. It's not something we expect you to do in your head. With your calculator, doing the math, make sure your parentheses stay as is, and you're raising to the 4th power. If you do, then you should have gotten an answer of $5,088.13. So you can see that our 4,000 originally grew about $1,088 over the course of 4 years. And that's with a 6.2%, which currently is better than you're getting at any bank. Okay, let's reset that. And again, go for the same thing. Let's actually move this down so we got a little more room to write this time. This time, you're buying a $1,050 stereo system in December on a credit card. So we're going to do the same thing, but now this is like paying the debt loan situation. With an annual rate of 15%, you pay it off in May. How much did you really pay for the stereo? So some people would say, well, $1,050. No, because you waited and used your credit card and paid it off, then you're also accruing some interest, which you really have to take into account. So here we go. Start with your formula. A equals P. Well, our investment was $1,050. That's how much we put on the card, basically, times 1 plus in December on a credit card with an annual rate of 15%. So our rate would be 0.15. Remember, change it to a decimal. How much did you really pay? So this is an example of a card where we're paying by the month. So that would be monthly, which is 12, to the power of 12 times. Now it says you bought it in December. So January, February, March, April, May. That would have been 5 years, or 5 years, 5 months later. So do the calculation. With your 1050, 1 plus 0.5, I'm doing it as UR. Could have done it up on the board there, I forgot. 1050 times 1 plus 0.15 divided by the 12, close your parenthesis, and raise it to the power of, if you don't multiply that out first, you are going to have to put the 12 times 5 in parentheses on your calculator. But 12 times 5 is 60, so we raise it to the power of 60. And did you get, remember your calculator doesn't know you're dealing with money, so how much did you really pay for that stereo? You know what, because I got a little different answer. I think annual rate of, I wonder if I'm going to change that to a, as credit cards are usually monthly, I'm going to change this to 1 plus 0.15 to the power of 5 instead of doing it monthly. I just assumed the credit card was by month. And we're getting a different value there also. Hmm. 50. All right. Next one. They're going to be talking about something called effective yield. This used to be big when people were talking about banks and being competitive and who's going to give you the best bank, especially when banks were first around. On the effective rate here, the effective yield is the rate of interest earned after all your compoundings have taken place in 1 year. And we're going to figure this and figure out what would really happen. And on an effective yield, it's easy to do, and we only calculate $1 over a period of time. And right now we're going to say we have an account paying 3.25% compounded quarterly. Find our results for $1. All right, A equals P times 1 plus R over N to the power of NT. We've got A equals our $1 times 1 plus our 0.0325 is our percentage turned to a decimal. Compounded quarterly is 4 to the power of 4 times 1. We're only going to do it for 1 year. So you multiply that out, and it gives us about $1, and you can see 0.0328999 cents. But remember, subtract that original amount that we put in there, so that dollar's gone, and we'd be looking at a 0.03289-ish. So from there, we've earned, in terms of money, about 3 cents. But take that decimal and change it back to a percent by moving it 2 places to the right. And we're really looking at 3.289-ish percent, and rounding that to the nearest hundredth, 3.29%. So effective yield, it really grew by 3.29, even though they originally told us that it was going to be 3.25. So it actually grew bigger than what they told us. And that's the whole idea. Effectively, it should grow larger than what they're telling you. Not by a ton, but by a little. All right, there might be a few problems that talk about past tense, going back in time. So in this case, think of P as the principal or as the present amount. You can work this one both ways. So maybe probably should divide this so we can do that. A CD paying 6.25% compounded annually has matured after 10 years, giving the owner $10,000. How much was invested 10 years ago? So some of you would say, well, $10,000 is what is currently in our account. We do what we were just doing. P was what we don't know because it says how much was invested 10 years ago. We do know 1, that's part of the formula, plus R, our rate is 0.0625, over N, 10 years, compounded annually, so that really is a 1 to the power of 10. Right, so you would have to undo that. So first you'd probably deal with this multiplication, find that number, bring it over here and divide that into the 10,000 and give you a p-value. So you could do that. But here's another new, maybe not as difficult process. Think of P as that current present amount. So we're going to go A equals that 10,000, which is our current amount of money it has been invested, times 1 plus R, the rate, 0.0625. Annually, it's 1 to the power of 1 times 10. But because this was 10 years ago, if we make it a negative 10, the calculation, I don't like the way that looks, the calculation would go backwards and undo the calculation. So remember, negative exponent, reciprocal work. So it would go back and undo that multiplication, exponentiation, compounding with a division style process. So let's do either one of these. We like the new way to write it, so let's go with that one. Just to show you, it can come out. Okay, I got $10,000 times, in parentheses, 1 plus 0.0625. Close the parenthesis. Raise that to the power of negative 10. And we should be looking at, and again, it works nicely. It does that calculation for you. A equals about 54.53, so $5,453 and about 94 cents. Now, I don't know if somebody would have come in and just put their piggy bank down or whatever. That's sort of an odd amount to invest, but it typically could have happened because you can invest any amount of money. But it's a good chunk, and then 10 years, you can see it turned into that $10,000 we have right now. So you're going to be doing several different real-life problems like this, using your compound annual compounding formula, general compounding formula, and going back in time possibly, or going current time. So see what you get, and we'll take questions in class.